Algebra, Chapter 8, Section 3. We are going to be looking at a second kind of sequence. In the last section, you looked at arithmetic sequences where we were adding the same thing each time to get our next value, and that was called the common difference. Well, we are going to be looking at what are called geometric sequences where we are multiplying by the same thing each time. So let's say I start with 2, and then I get a 6, and then I get an 18, and hopefully the board will wake up here and start working. Next comes a 54. Can you tell what is happening on this sequence? Well, hopefully you can tell we are multiplying by 3 each time. And we have a name for the value that we're multiplying by. It's called the common ratio. The common ratio can be found by taking any number in the sequence and dividing by the previous number. If I took 18 and divided by 6, I would get 3. I can take any number in the sequence. I can take 6 and divide by 2. Common ratio, 6 divided by 2. And there's my board going slow again. There we go. Equals 3. Common ratio, same value no matter which one we use. Here's the formula for it. A sub I plus 1, that means the next term after the A sub I, divided by the A sub I term, the previous term. So we get that common ratio. They're called geometric sequences. Just like on the arithmetic sequence, for an nth term, or the general expression, we had an equation that would find us the third term, or the second term, or the fifth term. Well, there is an nth term formula for geometric sequences. You need to memorize this one. A sub n, any term can be found by taking a sub 1, the first term, times that common ratio raised to the n minus 1, which means 1 power less than the term we are trying to find. If I use these values up here, let's see if we can generate this number 54 using that equation. Well, that happens to be the fourth term. N would equal 4. 1, 2, 3, 4. So if I use n equals 4 in this formula, let's see if we can get that fourth term. So a sub 4, the fourth term, would be a sub 1, our first term. What was our first term? 2. 2 times our common ratio. Our common ratio is 3, raised to the n minus 1 power. If I'm on the fourth term, 4 minus 1 is 3. Well, 3 cubed is the number 27. 2 times 27 equals 54. Check, it works. So make sure you know that formula to find any term in a geometric sequence. So trying these problems. So let's find the nth term, whichever term they happen to tell us, of the geometric sequence, whose first 3 terms are as follows. So on part A, well, I need to know what is that common ratio. So I can take any term, I'm going to take the 8/3, and divide it by the term before. Now, when we have fractions, we don't divide by fractions. So instead of dividing by the 4, we do the math by multiplying by the reciprocal of 4, which is 1/4. So instead of dividing by 4, I'm going to multiply by the reciprocal. Well, this would reduce. 4 goes into 8 twice, so multiplying it together would give me a common ratio of 2/3. So now they want us to find the nth term, or the expression for the nth term. Well, here, let's write the original, the one you have memorized. A sub n equals a sub 1 times r to the n minus 1 power. That's what we're filling in. So a sub n equals our first term. Well, our first term is 4 in this one. Times our common ratio. We just figured out our common ratio was 2/3, and it would be raised to the n minus 1 power. That would give us any term, the nth term formula. Part B, same idea. I need to find the common ratio. Well, I can take -10, divide it by 5, -2, there's my common ratio. So I can fill it in. A sub n, the nth term, is the first term, which is 5 in this case. times my common ratio, which is a -2, needs to be in parentheses because that -2 is all raised to the n-1 power. There's our formula. That will find us any term that we want in that geometric sequence. Example 2. Determine whether the sequence is a geometric sequence or not. Well, let's look at these first three values that they have over here. Is there a common ratio? Well, I can take -2 and divide it by 4, and that would be a -1/2 if I reduced it. And then check, if I take 4 times a -1/2, do I get a -2? Yes. If I take -2 times -1/2, do I get a +1? Yes. That seems to be working just fine. In fact, they've written the nth term right here. There is the common ratio, -1/2. 4 is the first term. -1/2 is the common ratio raised to the n-1 power. Yes, this part A checks out just fine. That is geometric. Let's look at part B. If I take 4 divided by 1, I get 4. If I take 9 divided by 4, I get 9 divided by 4, or 2 and 1/4, but it's not the same value. Not the same value. It's not a geometric expression because I'd have to have the same ratio every single time. That one doesn't fit. On the arithmetic series, you may remember we had a formula for the sum, a partial sum of the first 10 or something like that. There is a formula for a geometric one. So here's another formula to memorize, the sum of a geometric sequence. A sub 1, and then in parentheses, 1 minus r to the n. N is the number of terms we have in our sequence we're trying to add up, divided by 1 minus r. As long as the common ratio is not 1, this formula would work. Otherwise, you'd be trying to divide by 0. Part A. Find the sum of the first 4 terms of the geometric sequence that looks like this. And they've given us these numbers, and they've given us the expression. So in part A, as I look at my formula, the sum of the first 4 terms, well, a sub 1, what's our first term? 5, times 1 minus my common ratio. What am I multiplying by each time? Well, you can probably tell from the sequence of numbers that we're multiplying by 3 each time. You also could recognize it in the formula. 1 minus 3 raised to the 4th power, because we are finding the sum of the first 4, divided by 1 minus the common ratio, which is 3. And now we just need to simplify it. So 5 times, now we have 1 minus 3 to the 4th. 3 to the 4th is 81. 1 minus 81 is a -80. Divided by 1 minus 3 is a -2. Do your math on that, and you should get 200. Filling in the formula. Part B. Evaluate this finite, which just means it's not infinite, but doesn't go forever, finite geometric series. They've written it in summation notation. The summation, so we're adding all these things together. That's what a partial sum is. And they give us the general expression right here, the equation that finds every term, and they say we're supposed to start with the first term, and we end with the 17th term. So if I fill in my formula, sum of, well, I have 17 terms. If I start with 1 and go to 17, sum of 17 terms. And I'm using this formula up here. A sub 1, first term. Well, I need to figure out what my a sub 1 is. So off to the side, let's figure out what our first term is. This is the equation that gives us each term. So a sub 1 is where n equals 1. 3 times 3/4 raised to the, well, if n is 1, 1 minus 1 is 0, raised to the 0 power. And what is anything raised to the 0 power? 1. So this is really 3 times 1, or just 3. There's our first term. So a sub 1 in my formula is 3. Times 1 minus my common ratio. 1 minus, what's my common ratio? Well, if I come back to that general expression, my common ratio is right there. In fact, we could have even figured out the first term right there. Common ratio is 3/4. 3/4. Raised to the nth, 17th power. Close it up, and we're supposed to divide by 1 minus our common ratio. 1 minus 3/4. Now, this is a problem where you're probably going to want to go to a calculator on. And you'll want to be able to use your parentheses judiciously, correctly, in the right locations. Why don't some of you start, and I'm pulling up my calculator. Hopefully it won't take too long to get going. And I will enter this. You are going to need a set of parentheses around everything in the numerator. You have to tell your calculator where is the numerator. You will need a set of parentheses where the parentheses are in the problem. And also around the 3/4, because we have to tell it the 17th power is going on the 3/4 only. And then you'll need a set of parentheses around that denominator, or you could do that in your head. 1 minus 3/4 is 1/4. So either in your head or using parentheses on your calculator. And my calculator is coming up very slowly. So some of you have been working at it and hopefully have the answer already. But your solution to this one, let me round it off, 11.91, if you round that off. And maybe my calculator will pull up here in a bit. And I can come back and enter that and show you how that one works. But I put the parentheses in the area, in the locations, in the places where you would need to. All right. Let's look at a continuation of a series that I keep going more and more and more and more on. If we took that last one that we just did, I think it was the last one, and if I took 3 terms, notice the sum is 3.9375 and a bunch of zeros. If we took 6 terms, it becomes 3.999, etc. If we took 9 terms, 3.99998474. If we took 12 terms, 3.9999999. What are we getting closer and closer to, and what's happening to that common ratio? Let's look back at our sum formula for a geometric partial sum. A sub 1, our first term, times 1 minus r to the nth power divided by 1 minus r. And let's look at why this sum keeps getting closer and closer to some value. In fact, if you were going to round this last number off, you would probably guess that it's getting closer and closer to this number 4. So let's see why we get closer and closer to a number as I do more and more terms. Well, the reason, the key to it all, is right here, that r to the nth power. On that last one, what was our r value on that last one back here? Ooh, everything's going slow. There we go. It did come back. 3/4. 3/4 was our r value on that last one. If we took 3/4 to the first power, well, I get 3/4. If I start taking 3/4 to larger powers, let's say I raised it to the 10th. Maybe even write this as decimal. 3/4 is 0.75. If I took 3/4 and raised that fraction to the 10th power, do that right quick, 0.0563 approximately. 0.0563. Did that get to be a smaller or did it get larger as I raised the 3/4 to a larger number? Hopefully you recognize that that is getting to be a smaller number. How about if I took 3/4 and raised it to the 100th power? See if our calculators will handle that even. If we take 3/4 and raise it to the 100th power, well, 3.21, but then it has this nice scientific notation, times 10 to the negative 13th. In other words, I would need 12 zeros after that decimal before I even start my 3. Notice how that ratio, that 3/4, is getting tinier and tinier and tinier and tinier. Essentially, we say that that ratio, if I kept doing it, where I was taking that 3/4 and raising it to a higher and higher power, in fact, if I raised it to an infinite power, it would just give me 0. And so if that goes to 0, let's come back and look here. If this goes to 0, 1 minus 0 is just 1. And a sub 1 times 1 is just a sub 1. And on the bottom I have 1 minus r. And I have done it to an infinite number of terms. Surprisingly, if we have a geometric sequence that is an infinite geometric sequence that we do forever, we never stop it, and we add up all those infinite number of terms, it will equal a value. It will have a limit to it. And this one right back here, it has a limit of 4. And how we can find our limit is this new formula. A third one to memorize today. I'm going to put a little infinity symbol underneath that S, even though they don't have it. The sum of an infinite geometric series. Now this is only going to be true for certain common ratios. It's very important that our common ratio has an absolute value less than 1. Right up here, our common ratio was 3/4. That's less than 1. If your common ratio is bigger than 1, or less than a negative 1, whatever absolute value gives us bigger than 1, then you just keep getting bigger and bigger and bigger and bigger because your numbers keep getting bigger. And so if you add them up, you keep getting a bigger and bigger answer. You won't have one answer to an infinite geometric series when the numbers just keep getting bigger. But here the numbers keep getting smaller with that common ratio, and so we end up having a sum. So as long as it verifies that it's geometric and the common ratio has an absolute value less than 1, we can use this new formula and get a sum, get what it goes to. So they say, hey, here's an infinite geometric series. We start at 1 and we stop at infinity. Some of you might like to go ahead and write all those down. Let's evaluate the sum. Can I get a sum? They say it's infinite. Well, if it fits right up here, I can just use the nice formula, a sub 1, 1 minus r. But my r value is my check. What is the common ratio? Well, I can look at this formula and tell the common ratio. It's the thing that I keep raising to a power, a higher and higher power. And so negative 2/3 is my common ratio. So the question is the absolute value of negative 2/3 less than 1? Yes. 2/3 is less than 1. So it fits. I can use my formula. So what's my first term? Well, I can actually read it from the formula, but let me go ahead and put this 1 in and see what happens. If I take, trying to find my first term, if I take that negative 2/3 and I raise it to the 1 minus 1 power, 1 minus 1 power, well, that's 0. Anything raised to the 0 power equals 1. 1 is my first term. You may recognize that there's an understood 1 right in front of that. So our first term is 1 divided by 1 minus my common ratio. My common ratio over here is that negative 2/3. Negative 2/3. So let's simplify this and see what our infinite sum is. 1 divided by 1 plus 2/3. Well, 1 plus 2/3 would be 5/3. 1 and 2/3, 5/3. We don't divide by fractions. We'll take that 1 and multiply by the reciprocal. 1 times 3/5 is 3/5. And so if you started this expression and added all the terms you could generate if you did it infinitely, it would add up to the grand total of 3/5. Now some of you might be saying, now hang on. Our very first term was 1. We're already bigger than 3/5. Well, your next term is going to be a negative number. It's going to alternate between a positive and a negative number. And so we start with 1, but we actually start backing down and getting smaller on this one. We can use this idea of infinite term sums to help us rewrite certain decimals as fractions. Now, you may know already what 0.3 repeating is. 0.333, 0.3 repeating, you probably already know that fraction equals 1/3. Let's see if we can figure out how this is an infinite geometric series, and then we're going to use our formula and see how it gives us 1/3. The first term in this number we would call 0.3. Our common ratio, well, let me say the second term first. Our second term in this formula we would call 0.03. If I just added those first terms together, the 0.3 would give me that number, plus 0.03, I'd now be up to that number, 0.33. 0.3 plus 0.03 is 0.33. My next term, third term, would be 0.003, because adding that to what I had previously would give me that next 3 right over here. So I can just keep on doing that forever, and I keep getting more 3's. Now maybe I can see what my common ratio is. What do I have to multiply this first term by to get this second one? Well, I moved the decimal one place to the left. That means it's 1/10 of what the other one was. 0.3 times 1/10, or 0.1, would be 0.03. Times 1/10 again would move it one more decimal place to the left. There's my common ratio. That's a common ratio that is less than 1, or whose absolute value is less than 1. So I can use my infinite sum formula, a sub 1 divided by 1 minus r. So our first term, 0.3, and now I'm going to write that as a fraction because it will be easier to simplify. 0.3 is 3/10. First term, 3/10, divided by 1 minus my common ratio. And our common ratio is 1/10. I'm going to do that denominator. 1 minus 1/10 is 9/10. So I have 3/10 divided by 9/10. I'm going to multiply by the reciprocal. Instead of dividing by 9/10, 10/9 instead of doing that. These reduce. 10's going to itself 1. 3 goes into that 9 3 times. And guess what we have? The 1/3. So that formula will work on any repeating decimal. It doesn't even have to be the same number. Any repeating decimal will have a fraction that relates to it, or it is a rational number. So we can find that rational number. So let's try that on a little more complicated value down here in example 5. Notice in example 5, 3, 4, and 5 are not repeating. Only 4 and 5 are repeating. In other words, it's the number 0.345, 45, 45, etc. It's that 4, 5 that repeats. So this 3 is outside of our repeating part. So when I go to write this, I need to separate that 3/10. 0.3 is 3/10. I need to separate that 3/10 and then add what I find to be the fraction for the rest of the repeating decimal. And my very first value would be, my a sub 1 on this would be 0.045. Because I need a 0 where that 3 is, so when I add that 3/10 to it, I get that 3 back. My next term, my a sub 2, would be 0.00045. Notice I had to move 2 more places over because there were 2 numbers that would have fit right there. So I am moving 2 decimal places over. I'm actually moving 2 decimal places to the left. I should have made my arrow on that side. So if I'm moving a decimal 2 places back to the left, that's 1/100th. I'm dividing by 100. So let's go through our infinite sum that we're going to do right here. A sub 1, 0.045. And I guess I should write that as a fraction, just like I did last time. That's 45, think of the decimal place. This number right here is 45 thousandths. 45 thousandths. Divided by 1 minus my common ratio, which is 1/100th. So again, in that denominator, we can take 1 minus 1/100th, and we'd get 99 100ths. So I still have this 3/10 in front, that's not a repeating part, plus this infinite sum that we have. 45 thousandths divided by 99 hundredths. And we don't divide by fractions. We're going to multiply by the reciprocal, so 100 over 99 instead of doing that division. And I can do some reducing. So those two zeros are going to knock out two zeros right there, so that helps out. So far, in my head, I have 45 in my numerator, and I have 10 times 99, so 990 in the denominator. And then I need to reduce that again. Happens to be 1/22, 1 over 22. 45 goes into that, and 990 22 times. So this part is 1 over 22. So I have 3/10, the non-repeating part, plus my repeating part, which is just 1/22. And if you do 1/22, you should get that 0.0454545, etc. That's the fraction that matches the repeating. And now I need to add those two fractions. You can get a common denominator. You can use your calculator to help you get those two fractions added together. 19 over 55. Verify it. Take 19 divided by 55, and you get this number, 0.3454545, etc. So we can turn any decimal that has a repeating section or repeating parts to it into a fraction or a rational number, which is what it is. All right, we're going to have a couple of applications. Good news, you do not need to memorize these formulas. You do need to know how to use these formulas. There's something called an annuity. An annuity, probably the most common way that you will run across an annuity, is when we have retirement. Unable to save file. Hopefully nothing is going wrong. Is when we have retirement accounts from a company. If you work for a company who provides you with a defined contribution plan, it's called, they will every paycheck give you so much money to go into in a retirement account. So let's say you get paid monthly, so every month they will contribute a certain amount, and usually they match a certain amount of what you are voluntarily going to contribute. So you decide you're going to pay 3%, maybe they match half of that, so they'll pay their portion plus another 1.5%, half of what you gave, and that all goes into an account that is then built up through your working years, and when you retire, that money becomes your retirement savings that you are going to use to live on. So many companies have annuities. You may have heard of the letters or numbers letters 401k. Pretty common. There's a 403b. It's the same thing. 403bs are for nonprofit organizations like the Academy. I have a 403b from the Academy for my retirement. 401ks are the same thing, but they're for for-profit businesses. Certain categories in the tax law that allows you to do these things and not pay taxes until you retire on it is what it is. So let's see how this formula works. R in this formula is your rate, but the rate is the interest divided by the number of times a year you put the money in. So I is going to be your annual interest rate that you are earning on this annuity. Maybe it's 7%. So it'd be 7 divided by 12. So I is the annual interest rate, they say right up here. N is the number of times or compounding periods that you are going to put it in, and compound, they figure the interest and put it back in. T in the formula is the number of years, or I guess it's not in the formula down there. They use the letter M up here. They use the letter M in the exponent. Right there's an M. NT, number of times a year times the number of years you leave it in. So T is the number of years. So if you do it monthly, 12 times a year, for 40 years, 12 times 40 is going to be what that exponent ends up being. And P, that's how much gets deposited every time you do this, every month or every 2 weeks or every 6 months, whatever it happens to be. And the A then will be the amount of money, the final amount of money you have at the end of those years, 40 years, whatever it is, in that annuity. So let's try it out. An employee savings plan allows any employee to deposit $25 at the end of each month into a savings account, happens to be earning 6% annual interest. It's compounded monthly, and we only have the formula where it's compounded the same number of times as you're depositing the money. Find the future value, and it's called future value because it's a value of the money in the future, of the savings plan if the employee makes the deposits for 10 years. So they only stay with this company 10 years. So let's try it out. Filling in the values up there. A equals P. How much are we putting in? We're just putting in $25. You better put in more than that if you're planning on retiring, but that's all right. Times, and then we have in parentheses 1 plus R. Now how are we going to get our R? We're going to have to take the annual rate and divide by the number of times a year we're doing this. Annual rate, 6%, needs to be written as a decimal, 0.06. Divided by the number of times, well, we're doing it monthly. That would be 12 times. And that has to be raised to the M. What is M? M is the number of times a year times how many years? Well, we're doing it 12 times a year for 10 years. Off to the side, it's easier if you figure out this number by itself. 12 times 10, 120 is going to be that exponent. 12 times a year for 10 years. Minus 1, close our brackets, and all of that is divided by the interest rate of 0.06. This is a problem that you are going to need to be able to enter all at once in your calculator so there is no rounding error. So I hope my calculator will function properly for us. You need to tell the calculator where the numerator is. You'll need a set of parentheses that begins and ends with everything in between. We will need a set of parentheses right here, just where they have the brackets. And we'll need a set of parentheses where they have those parentheses, exactly how they have it. You don't need anything on the denominator because there's only one value down there, so the calculator understands what is in that denominator. So let me try it out. See if we are going to work. Enter it in your calculator. You need to verify that you are entering it in properly and you can get the right answer before you hit homework or you hit tests. Start parentheses, 25. Start another set of parentheses. There it's coming. Start another set of parentheses. 1 plus 0.06 divided by 12. My computer is determined to be very slow today. Close parentheses. Here's where our exponent of 120. Need to raise it to the 120th power. Minus 1. Calculator knows the exponent is only the 120. Then I need to close parentheses around that numerator. That's my last set of parentheses on top. Divided by our 0.06. And hang on, that's not 0.06. I almost have the wrong number. That's an R down there. It needs to be I over N, interest rate over 12. So we do need a set of parentheses right down there. So my apologies if some of you were already working on your calculator and you were not getting the right answer. So let me see if I can get my calculator back running. Divided by, start parentheses, 0.06, divided by 12, close the denominator, hit our equal sign, cross your fingers. Actually, it should work just fine. That is the number you should be getting. I'll try to capture that. It doesn't seem to be wanting to do very quickly for me, but it's thinking about it. I'll try it again. Capture. There, it worked that time. That gives you time to try to correct your errors maybe. We'll see if I get my paste to show up. Now we're dealing with money, and so we are going to round this to the nearest hundredth. Try it again. Cane. There we go. So there's everything written out for you. So you would have $4,096.98. And these answers should be correct to the penny. So if you leave it all in and do it at once in your calculator, you get the correct answer. If you're entering things in along the way, one piece at a time, and trying to round off some of those values, you're not going to get the correct answer out of it. So it needs to be able to be done with no rounding until you get to the very final solution. So over $4,000, just starting at $25 a month. And obviously, if you deposit more money in a month, you're going to get much more than $4,000 at the end. And if it's longer than 10 years, you're going to get much more than $4,000 if you take longer than 10 years. And I'm slowly saving this, we hope. There it appears to be going. Our next example is stock valuations. And again, you don't need to memorize this formula, but be able to use the formula. I think you understand what stocks are. Publicly traded companies, public companies, let's take Walmart, since that's kind of our close neighbor, and quite a successful company. Walmart allows you to purchase part of their company by stocks. And if you buy even one share of stock, then you can go to their shareholders meeting that they have annually and invite big people in and try to wow you with how wonderful Walmart is doing. But how do you know if you should buy stocks or not? What this model, this equation does, the Gordon model of stock valuation, it says, well, figure out how much interest you think you need to be earning on your money. What sort of return do you need to be earning? And then once you know what sort of return you want to be earning, well, then we can figure out if a particular stock should be purchased and at what price should you purchase it, because the value of the stock goes up and down. There's something called dividends that most publicly traded companies pay out. If they have made money during the year, then a certain percentage of however many stocks you own, the value of those, will be paid to you in cash. So right here, they are saying we have a dividend D in our formula, and the formula we're working with is this formula right over here. And so we have a dividend D, that's how much money per share of stock that a company happens to be paying. And then we have a variable G, so D is our dividend. G is going to be the expected percent growth rate of that dividend. So maybe you expect it to be growing at 5% a year, your dividend, or 10% a year, or something like that. I is the growth rate the investor requires. In other words, you've decided if I'm going to invest my money, I need to have at least a 12% return on my money. So let's try it out. See if we can make it work. Suppose a stock is paying, example 7, a dividend of $1.50. So for every share of stock you own, at the end of the year, they're giving you $1.50. It's estimated that the dividend will increase 10% a year. Now, obviously, you cannot tell the future, but it appears to be that, hey, we can expect it to increase 10% a year. This investor wants to have a 15% return on their money. Not that they're greedy or anything, but they just think they ought to be getting 15% back on their investment. So using the Gordon model of stock valuation, determine the price per share the investor should pay for this stock. All right? Now this started out as an infinite sum. Notice it's an infinite sum right here. They simplified it down to the formula we are going to be using, but that's why it's in this section. It's an infinite sum is where it comes from. Okay, so D, our dividend, $1.50, 1.5, times 1 plus G, how much we expect our dividend to grow, 10%, 0.1. 10% needs to be written as a decimal, 0.1. Divided by our our I minus G. We're using this one, almost went to the wrong one. We expect an investment return of 15%, 0.15 minus how much we expect the dividend to grow, which was 0.1. We're going to put that in parentheses. And we will see if we can't calculate, well, at what price am I going to be ready to, I can find my calculator, am I going to be ready to purchase this stock? So let's try it out here. And 1.5 in this case doesn't need to be in parentheses. You may put it in parentheses. Parentheses, 1 plus 0.1. Ooh, I guess we could do that in our head pretty easy. 1.1. Since I use parentheses, and I'm going to have to close them. Divided by, I need parentheses on that denominator. Tell my calculator that both of them are in it. 0.15 minus 0.1. Well, we could have done that in our head. 0.15 minus 0.1 is 0.05, but we'll let the calculator do it. We get a solution, and something either I wrote the wrong number last time. I wrote the wrong number last time, I think. $33. $33. So what is that telling me? When I look at the stock market and I discover that this stock that I was interested in has dropped below or at least at $33, then it is worth it for me to purchase it. If the stock price is higher than that, it's not worth it to me. So according to Gordon's model of stock valuation, it can tell me when I should be purchasing that stock. I believe, oh no, there's one more thing. Multiplier effect. Oh yeah, this is a good economics one. Multiplier effect. Here's the idea. Let's say the economy is not doing very well. So recently, we had an economic downturn a few years ago. Maybe about 7 years ago. I think it was 2007. And so the U.S. government wants to help jumpstart the economy, help get it going. So they want to give, push some money into the economy. Let's say they push in $1 million into the economy. Well, how much will that really affect the economy? Well, here's the idea. Of that $1 million, people are not going to spend every new dollar that they get. The economy's bad. They're going to be worried about saving some of it. So let's say the government thinks that 75% of what you have, I'm going to change this to 5 million, of what you have received extra, you are going to spend, and you're going to save 25% of it. So it'd probably be better if you did it the other way around, but 75% of it you are going to spend again. So if I spend 75% of it, well, that goes back into the economy again, of which other people that becomes income for, they will spend 75% and save 25%, and it keeps getting repeated. And so the multiplier effect says, I start out with a first term of $5 million, but I keep pushing back into the economy 75% of that over and over and over again. That's a common ratio. This is a geometric sequence. 0.75, 75% I keep pushing back into the economy. And we can keep doing this forever. It's going to be an infinite geometric ratio. So how much money is going to be totally into that economy? Well, what's the infinite sum formula? Well, a sub 1 over 1 minus r. So if I take that original $5 million, divide it by 1 minus, my common ratio is 75% or 3/4, easier to work with a fraction. 1 minus 3/4 is 1/4. I am not going to divide by 1/4. I'm going to multiply by the reciprocal, which is 4, and that 5 has now turned into $20 million. So by a government investment of $5 billion, the idea is that in the end, it really will end up being a $20 million boost into the economy. It's called the multiplier effect. I'm going to run across some that are similar to that. Let me give you another example that you're going to run across ones that are similar to this. Let's say they tell us we have a geometric series, but they don't let us know what the first term is. They let us know what the fourth term is. Let's say our fourth term is 8/9. And they let us know what the seventh term is. Seventh term, they say, is 64 243rds. And they want us to figure out what is going to be the fifth term. Well, goodness, how am I going to find the fifth term? Well, we do have a formula that says any term in a geometric sequence is the first term times a common ratio raised to the n minus 1 power. But I don't know the first term, I don't know the common ratio, all I know is I'm trying to find the fifth term. Well, we can use the idea of what a geometric sequence is to help us get both the first term and the common ratio. Remember, a geometric sequence is where I take a term, multiply it by the common ratio to get the next term. Then I multiply it by the common ratio again to get the next term. Well, if I want to get up to the seventh term, how many times will I multiply by that common ratio to go from the fourth term up to the seventh term? It'll be 3 times. 1 time will get me to the fifth, 2 times to the sixth, 3 times to the seventh. So I can fill in what I know. The fourth term is 8/9. I don't know the common ratio, but if I cube it, I then will get this seventh term, 64 over 243. So let's solve for that common ratio. Well, I need to multiply by the reciprocal. So I have 64 over 243 multiplied by 9/8 instead of, we needed to get rid of that 8/9, so we needed to multiply by that reciprocal, 9/8. And when we do that and simplify it down, we get 8/27. You can use your calculator to help you. Well, that's r cubed. So if I want r, I need to take the cube root of that 8/27. Cube root of 8 is 2. Cube root of 27 is 3. I just figured out what my common ratio was. And now that I know the common ratio, I can come back and get my fifth term. Because my fifth term should just be the fourth term times the common ratio. That's what a geometric sequence is. So my fifth term should be the fourth term. Back here, what was our fourth term? 8/9. 8/9 times our common ratio. Common ratio is 2/3. So 8/9 times our 2/3. 8 times 2 is 16. 9 times 3 is 27. We have 16/27. That would be our fifth term. Now let's say they didn't want just the fifth term. They wanted something like the 27th term. Well, you could use a similar technique, or you could come back and actually get the formula that makes it work. If I use the seventh term in this formula, my seventh term is 60, or let's use the fourth term, it's easier. Let's use the fourth term, it's a little smaller. If I use the fourth term in the formula, this formula right here, my fourth term is 8/9. 8/9 must equal, I'm using this equation right here. The first term, I don't know, a sub 1, times my common ratio, I do know my common ratio, we figured it out was 2/3. Raised to the n minus 1 power. I'm using this. Raised to the n minus 1 power. Well, it's the fourth term. 4 minus 1 is 3. That would have to be cubed right out there. So I could solve for my a sub 1. 8/9 equals a sub 1 times, if I cube this, 2 cubed is 8, 3 cubed is 27. We've seen that number before. I can solve for my 81. To get rid of my 8/27, I multiply by the reciprocal. So that 8/9, I need to multiply by 27/8 in order to get rid of my fraction. 8 cancels out, 9 goes into 27 3 times, and my first term, I just figured it out. My first term happens to be 3. So if I wanted the expression, I could find any term. I'm back up here, using this same thing right there. Any term is the first term, which I just discovered was 3, times my common ratio, which we already figured out was 2/3, raised to the n minus 1 power. That would be the equation that fits this one that we had. So there's a couple more examples that may be useful as you run across some of your homework. All right, you have your syllabus, and you can start working on Chapter 8, Section 3.